In this lecture, I want to take what we learned from the previous lecture and look at proposing, the mechanism for the Solvolysis reactions that we had been talking about a couple of lectures ago. So in this lecture, we're going to simply look at I don't mean to say it that way. We're going to quickly look at the mechanism of the Solvolysis reaction. Okay, so what I want to do is consider the reaction where we take our tertiary haloalkane again, and instead of having a negatively charged nucleophile, we want to add this to an alcohol. And we'll pick on ethanol. Okay, so just get some more lighting in here. Okay, so this will give rise to two products. This will have an SN1 product plus an E1 product shown here. So we have two products that form, one for each of the reactions that are going to occur together, which is the SN1 and the E1 reaction. I should also add that the ethanol is used as the solvent. So the solvent is facilitating the breakdown of the starting material to form each of the two products. So this is considered a solvolysis reaction. So let's propose a mechanism. What I alluded to that I should be more clear about is that a solvolysis reaction is a type of SN1-E1 reaction. And as a result, we should think, as we're considering the mechanism, about the carbocation. Again, this needs to be one of these knee-jerk reactions that we have. Whenever we hear the term SN1-E1, we immediately make note that we're running a reaction that's going to form a carbocation intermediate. And so, if we're going to form a carbocation, let's do that in the first step of the mechanism for both of these chemical reactions. So the first step is going to involve heterolysis of the carbon-bromine bond to give rise to a trigonal-planar carbocation intermediate plus a Br minus. Now, perhaps you're concerned about the negative charge in addition to the positive charge, and so maybe these could just snap back together. Like, I'm just going to delete this quickly after I draw it, but we could go this way, in which case we would just draw an equilibrium arrow. And if you'd like to really take that into account, we could consider the equilibrium process like this. Okay, now the equilibrium process is unfavorable to form the high energy carbocation intermediate, and that's reflected in the relative energy that we saw in the energy diagram that we talked about in the last lecture. The carbocation intermediate is higher in energy, but we will have some equilibrium concentration, though it might be small, of our carbocation intermediate, and that will be enough to engage in the SN1 and E1 reactions shown below. And what we get is a siphoning effect. The more carbocation intermediate you absorb, the more starting material you're going to take on and through into forming the carbocation intermediate. This kind of process of disturbing an equilibrium, reestablishing equilibrium is called Le Chatelier's principle. Anyway, a topic for a different day. So we have this carbocation intermediate, and now I'm going to label this as my SN1 reaction. Actually, I'm going to start with my E1 reaction. It's a little bit simpler for the case of the solvolysis reaction. So for the E1 reaction, what we're going to see is that our positive charge is going to be neutralized by loss of one of the vicinal hydrogens. It turns out there are actually 9 vicinal hydrogens in this molecule. I'm going to draw one down here. And so losing that, we're going to take the 2 electrons from the carbon-hydrogen bond and use them to make a carbon-carbon double bond in the product. That's going to give rise to a carbon-carbon double bonded product, which is an alkene, which is a typical elimination product, with H plus being a component of the reaction. Now, I wanted to start with the E1 reaction mechanism because we actually had already done this. We did it in the last lecture, so hopefully it's somewhat familiar to you. But before we go into the SN1 reaction, we have to reflect that before I didn't actually show a nucleophile when I talked about the SN1 mechanism. I had some nuke minus, right, that just combined with the positive charge. We're going to do that here, except note that the alcohol is actually a neutral nucleophile. So let's go ahead and look at that. So this is going to be the SN1 reaction. So I'll draw my carbocation. The carbocation is used for both the SN1 and the E1 reactions. And I'm going to add that to my nucleophile. In this case, the nucleophile is just the solvent of the reaction, which is ethanol. Now, if you notice, this is a neutral nucleophile. There are no charges on the nucleophile, but all that a charge is, it's a label. It's an appropriate label. It tells us some interesting things about the molecule, but it's a label to tell us about atoms that have or don't have lone pairs of electrons and covalent bonds. And so whenever we have a negative charge attacking a positive charge, that's me showing an arrow from a negative symbol as opposed to a lone pair of electrons. In reality, it's the lone pair of electrons that do the attacking of positive charges, or there are electrons and bonds. So what's happening here is that the lone pair of electrons is going to engage the positive charge. That's going to forge a new covalent bond to give us a structure that looks like this. Now, instead of having two lone pairs of electrons, now the oxygen is down to one lone pair of electrons. Additionally, I show the ethyl group as coming along for the ride and attaching and still being attached to the oxygen, but we can't forget about the hydrogen atom. The hydrogen atom also comes along for the ride. We no longer have a negative charge to kind of deal with or tell us that we have an absence of a hydrogen. In fact, it's the presence of that hydrogen that allows this substitution reaction to happen at all. So the hydrogen is coming along for the ride. Now, what that means is that we have to now consider formal charges. If you look, we're overall +1 charged on the left, and as I have it drawn now, we're overall neutral on the right. Well, what's happening here is the +1 on the left is correct, but the neutral on the right is incorrect. The formal charge on our oxygen is, well, we have a group 6 element -3 bonds -2 unshared electrons. Those are going to be the 2 electrons that comprise the lone pair of electrons. That's going to give us a +1 overall charge, which goes on to the oxygen atom. So you could write +1, or you could just write a plus symbol. I'll just write a plus symbol down below. So my point is, we're actually not done. We're not done with the mechanism. We haven't formed the substitution product. The substitution product is not what I have drawn here. Let's circle that positive charge so I can see it clearly. Rather, the substitution product is the product where the oxygen is neutral, or where it has 2 lone pairs of electrons. And you could prove that to yourself. So formal charge is 6 -2, in this case -4 unshared electrons, which is 0. So right now we're at +1, and we just went through that calculation. So what's happening here is actually a very simple step. The oxygen has added to the positive charge. We saw that up above. The oxygen adds to the positive charge to give rise to an intermediate where everything, and the intermediate is right here, everything comes along for the ride, including the hydrogen atom. After we do the addition, we must lose that hydrogen through a deprotonation event. This is very similar to the deprotonation event or loss of hydrogen event in the E1 reaction, except the electrons between the oxygen and hydrogen jump down to form the second lone pair of electrons. Additionally, what that means is that the byproduct of this reaction is going to be an H+, which gets picked up and probably removed initially by, in this case, solvent molecules. So the excess of ethanol promotes the capturing of the hydrogen in the final step of the substitution reaction, and it also ensures that we have a really high concentration of ethanol to add the neutral, that is not good, nucleophile to our carbocation intermediate. And so this is the full mechanism for the SN1 part of the Solvolysis reaction. And what we need to do then is just slightly revise our energy diagram for the Solvolysis reaction. So this is going to be an SN1 Solvolysis reaction energy diagram. Now what we have here are we're actually going to form two intermediates. So if this is our starting material, our products are down here. We're going to have intermediate 1, and then probably lower in energy, though I wouldn't worry about Y too much, is intermediate 2. So intermediate 1 is going to be our carbocation intermediate, and intermediate 2 is going to be our oxycation, or oxygen-centered cation intermediate. Now we're going to go through some transition states. The first transition state is going to be higher in energy than the other two transition states. So this is TS1, TS2, and then TS3. So we updated our energy diagram. I'll just label the axes really quick. We updated our energy diagram because we had to capture the additional, call that free energy. We had to capture the additional intermediate that forms during the Solvolysis reaction because we have a neutral nucleophile that adds and eventually then loses hydrogen to give rise to a neutral product. It's important to note that TS1 is still the rate determining step. Okay. So that is a deeper look into the mechanism of the SN1E1 reaction as it corresponds to Solvolysis reactions. This is actually pretty true for most reactions that involve alcohols as nucleophiles or any other nucleophile that's neutral. We add, and then if we can, we lose hydrogen because that positive charge in the product we would like to deal with. And the easiest way to do so is to lose a hydrogen next to the positive charge, just as we've seen with vicinal hydrogens in the case of the E1 reaction.